Yes, sir. We were able to see.
The first quiz also you got to see the marks, right?
Yes, it has been released.
Okay, thanks. And we have decided the midterm exam to be on 13th or something, right? I think I've marked our calendars also.
Yeah. Yes,
Yes,
sir.
it's 13th afternoon.
13th afternoon. Okay, great. Okay, so let's get to somebody has raised their hand. Arijit, yeah.
Sir, maybe a logistical request, if feasible, otherwise please reject, because this 4 to 8 or 2 to 6 is like a festive for us, like Durga Puja and all the Sera. So that assignment time, can it be increased by report days? Just a request. If not for feasible, please ignore.
What can what?
That
Your voice got
assignment deadline is 9th, I believe, right? And
correct.
2 to 6 is somewhere is a festive session for most of us, like Dasera, Durga Puja, etc. So can it be increased by 2-3 days? I mean the timeline, because we may not give the complete hours should be given to this project during that time. It's just a request. I mean, if not possible, please ignore.
See, what happens is no, if I move it, then the entire schedule has to be rearranged. So kindly excuse me on that.
Okay.
Okay, let's get started. You don't see my screen.
No, sir.
Okay. So today's agenda is that, as I said, we will move on to the next class of models, which are variational autoencoders, which also happens to be the baseline for the state-of-the-art generative image generative models called diffusion models, which we will see next. Okay. So before we go there, we just take some 10-15 minutes and quickly finish this domain adversarial networks, right, which was left out the last time. Uh, oh, always there. Still it is. How do I hide this? Yeah, somebody asked me to center align this so that get cut. Doesn't even know how to do that.
So you can zoom it. Yeah. In the view, you can make it 100%.
Come again?
On the top, you will see home, insert,
View.
drop,
Yeah.
view, 100%.
Okay, thanks. This should be enough. Okay, so we will start with this domain adversarial networks, okay, also called DANS. One of the uh, powerful applications of adversarial learning other than generative modeling. And also, right before we start, I hope that you have started with the assignment. And if there are any questions, you can let me know, or TS also know.
Sai pinged and TA, but no one replied.
Oh, is it? I'll ask Chandan to do it. So last tutorial was done on CNNs and PyTorch, right? Was it useful?
Sir, it is useful, but sir, in the tutorial, can we have some sample output of the first question? Like at what level we have to optimize
You mean in the assignment you are saying? See, what
assignment?
I have observed is that that this animal data set, right? Because there are multiple classes there, about 90 classes. Unless you have a very deep architecture and you do a lot of hyperparameter tuning, you don't get very good generated images, right? But if you get images that are like uh,
Butterfly.
somewhat looking like butterfly, you will definitely get. For that data set, you will get good images. Not for the first one. There are two data sets that we have given, no?
Correct.
Yeah, for the animal data set, the images that are generated are like somewhat like looks like animalish, but you need a lot of resources and deeper architectures to get very good results. Okay, in fact, uh, okay. So have I talked about FID in this course?
No, sir.
Not
No,
yet.
sir,
No,
Not
sir.
yet.
it is
Okay, I
planned for
think
today.
I'll have to do that today as well. I've not told you about the Wasserstein's metric also, no?
Yes, sir.
No, sir,
Not
we
covered.
haven't.
Sir, if the
Too many
animal
things to cover.
data set is hard for question 1 and 2, then why are you asking for the other questions?
Come again?
Like if animal data set is hard to train given the compute resource we have, then for other questions also like third, fourth, and waste all, like we'll have to use the same data set, right? Animal. Then
Yeah.
we'll have a poor result there also if we train
That's
lesser.
okay.
Okay.
That's okay. See, the assignment grading will not be based on the quality of your generated data anyway. It's not about results. So yeah, but it has, I mean, I have deliberately chosen that data set because I want you to appreciate the fact that if there are too many classes and data has a lot of modes, right? Building a generative model is difficult, especially using adversarial training. So we will use the same data sets for VAEs and diffusion models, and you will see that it will improve. It was deliberately done. Yeah.
Sir,
Okay,
the confirmation what we were trying to ask, the butterfly data set is for only the 1 and 2.
correct.
From the third onwards, we need to use the animal data set. The first GAN, we need to use the animal data set and see how the outcomes are coming, even the FID calculation, everything.
Correct.
Okay, that was a confusion. Okay.
But for the first and second question, you will have to use the animal data set as well, both of them.
Oh, yeah, we need to train it for the other
Correct.
things. Yes.
Correct.
Okay. But the generation may not be so accurate. Okay.
Yes. Okay, so let's maybe continue quickly. Yeah, go on, Gopal.
Yes, sorry, sir, one more thing. I noticed, sir, in the original GAN paper, the model was basically on a 64 by 64 image. The moment I scale it up to 128, right, I noticed the mode collapse becomes a lot frequent than 64 by 64. Like the performance is much better.
You mean
Any
the
reason?
DC GAN? DC GAN, you're saying?
Yeah.
DC GAN. Okay. Yeah. See, you can tweak. One thing that you can do is, if you start from 128, just have another downsampling layer and then use DC GAN on top of it.
Sure, sir. I tried that. I think it requires a little hyperparameter tuning to get it right.
Correct.
Okay, sure.
Yeah, Balaji.
Yes, sir. My question is regarding the assignment. So in question 8, it is asked we should implement a decoder network. So should this be for the GAN in the first question or the conditional GAN?
It's in the GAN in the first question only.
Okay. Okay. Thank you.
Satya?
So this is the instance of GAN, FGAN we discussed, right, where we use the junction, Shannon, divergence for the naive GAN. So actually, if I see that FGAN paper, right, sir, that is the GAN is separately mentioned and junction Shannon is also separately mentioned. So it's not that because of junction Shannon we are
Sure.
getting
Okay,
a
okay,
naive
I'll
GAN,
tell
right?
you. Yeah. See, okay, that's a good observation. See, the divergence that is used in the naive GAN paper is Jensen-Shannon divergence minus a constant. I think it's log 2 or something. Okay, that's the and it's JS divergence plus a constant. That is what the GAN objective is.
Okay. Okay.
Yeah. Okay, so let's maybe quickly go. There are too many things to discuss. Okay, let's get started. Yeah, it's charged. I said so. There is another application of adversarial learning, which is called domain adversarial networks. Okay, so here is the problem. So what you are given is you are given some data from a distribution called source distribution. Okay, X1, Y1, X2, Y2, up to Xn, Yn. Note that this is a supervised problem. This is drawn IID from a distribution PS, which is called the source distribution. This is source data. And there is another data that is given to you. You call X cap 1, cap 2, and XM cap. So this is sampled IID from PT, okay? And this is called the target data. Okay. You note that source data has both the features and labels. The target data only has the features and does not have labels. Source data is supervised. Okay. This is unsupervised. Okay. Now the goal of what is called as unsupervised domain adaptation so called as UDA, okay, is given TS and DT, okay, learn features or representations such that they perform well on both source and target data. See, oftentimes what happens is that suppose you want to, let me just show you an example. Suppose you want to you want to build a classifier. Hold on. Unsupervised. Show some examples and you understand. Give me a minute. I'm just looking for that image. Ah, yeah, this is good. Hold on, let me share my screen. You see my screen?
No, sir.
Now?
Now, yes.
Okay, so look at this. So there are these data sets, okay? There is MNest, there is USPS, something called MNest M, and there is the Street View house numbers data set, okay? Now, what you see is that all of these are semantically the same. The class wise, they all have the same, right? They have digits, okay? But if you build a classifier on, let's say, MNest and try to test it on USPS, it will not give you good performance. Okay. Now the goal is that suppose you are given data from MNest with labels and data from USPS without labels. That is the setting, right? Where you understood the setting that there is a source domain which has labels and there's a target domain which has data but does not have labels. Okay. Now the task is that you have to build representations such that a classifier that is trained on the source data does well on the target data as well. That is the problem setting. Is it clear? Any questions? So you have to ensure that the problem definition is clear. Then we will move on. Please ask if you have any questions. Can't see your. Yeah, Shivam.
Yes, sir. When we say we want to learn this on the model should perform well on the target distribution as well. Eventually, we will be passing target distribution back to the model to get the respective target labels, right?
Final evaluation will be done with target labels, of course. But while you are building the model, you don't have target labels.
Okay.
Of course, I mean, when you evaluate definitely it will be based on the target labels only. But yeah, yes, I don't see. Yeah, Satya, go on.
Sir, isn't it the cycle GAN? It's the same, right? Which you're doing. Only that we don't have the labels for the first data set.
No, see, in cycle GAN, the objective is to convert the source data to target data, right? Generate samples from target data. Here, you're not. The objective is not to generate the target data. It is to build a classifier or representation such that it does well on target data as well.
Okay. To produce a label over that target data.
Correct. Sanjit?
Sir, you answered my question. So basically,
Okay.
we are
Then
trying
let's
to.
move on. Then let's move on, please, because it's too many things to cover today. If I've answered your question, let's move on. Okay. So that's the okay, I'll have to share it again. That is the problem setting. See, there is also another class of problems, right, where you do not even have data from the target distribution. Okay. Those set of problems are called domain generalizations. This is domain adaptation. Suppose you don't have DT as well, okay? Then those class of problems are called domain generalization. We are not looking at domain generalization. Now we are looking at domain adaptation, okay? Where target data is also present, albeit without labels. How do you solve this question of how solve this problem? There are multiple methods that people have come up with. One of them is what is called as domain adversarial networks. Domain adversarial networks. Okay, what is done is the following. I'll show. So there is a feature extractor. Let us call that as some phi of x. This will take xs, which is the source data. I think let us okay, x and x cap, right? X is the source data, and it will also take x cap, which is the target data as input. Okay, it will give you the corresponding representations. So let's call it as ZS and ZT. And here. Okay, so this is simply a feature of extractor. So this phi is a function that will take x and that will give you some features Z. Okay. Then what we will do is there is a classifier, there is a critique network here or a discriminator network here. TW, this will take Z. So this will take either ZS, okay, sorry, CS and ZT. Okay, now I should say that here P of X is equal to ZS, okay, and P of X cap is ZT. Okay, that is how I have represented it. Fine. Now what I do is I will prime this thing. So this will be trained adversarially, okay? The GAN to ensure the distribution of ZS, okay, is close to the distribution of ZT. Correct? That is what if I train this adversarially, right? Then what happens is that the distribution of features PZS will be close to the distribution of PCT. Do you agree? See this whatever I have okay, maybe color. Marked with red color. This is a GAN, okay, to ensure PCS is same as PCT. Does it make sense? Now phi of X will become the generator, okay, and there is another discriminator that is there, and you are ensuring you are training it adversarially to ensure that PCS is equal to PCT. So what is the loss function here? The loss function would be that you learn your C star and W star, okay, such that minimize min over phi and max over W. You have an expectation of log of ZS, as ZS comes from PS, so you have expectation of log of 1 minus TW of ZT. This ZT comes from PCT. Are you getting it? So now if I train this as a GAN now, right, what it will do is it will ensure that the features for the source data and target data follows the same distribution. Does it make sense? Any questions on this? Go on, Indrajit. Indrajit, go on, please. I don't know if you any can you hear me, all of you?
Yes, sir.
Yes,
Yeah.
sir.
Okay, Raghavendra, go on.
Yes, in this case, the fee network that you have shown is kind of compressing
Generator.
the features. But I mean,
No,
is it reducing
no.
the dimensions or
Yeah,
increasing
it is. It is. Yeah. Typically, Z is less than dimensionality of Z is much less than that of X. It acts like a generator now. Yeah.
But I mean, it looks very similar to the discriminator, right? Because it's
No,
reducing the
no,
dimensions.
no. Just because it reduces the dimension, it's not discriminator, right? It is simply a neural network that transforms x from z, x to some one random variable to other. It can increase the dimension, reduce the dimension, doesn't matter. Of course, it is similar to discriminator in the sense that it reduces the dimensionality, but yeah, it is not a classifier, right? Which is trying to give a number between 0 and 1. Okay. Okay, so this is yeah, Vivek.
So what does it mean x and x cap? So are we passing it in sequence or are we?
Yeah, sequence, yeah. So you x, when x goes, zs comes out. When x cap goes out, zt comes out.
Zt comes out. Okay, fine. Yes.
Here, in addition to that, there's also a classifier here, okay? So this classifier, let's call that as h theta. This will take z as input, zs as input, and it will give you y as output, which is trained on only the source domain. Okay. Now this theta star okay, simply the minimizer of the cross entropy loss, which is ZS coming from PS, simply the minimizer of the usual cross entropy loss, okay, and trained supervised in a supervised way. Okay. Now the gradients flow like this. So the gradients for the Phi network, right? One, there is a backward pass from here to here. Okay, it is learned adversarially. And then there is another backward pass, which is supervised training that goes from here to here. So this is supervised classification. This is supervised, and this is adversarial. So now what is happening is that this Phi network is trying to learn features, okay, in such a way that one, it will ensure that the distribution of the features on source data and target data are exactly the same. This is done via adversarial optimization, and the features are also learned in such a way that it does classification well on source domain. Okay. Now during inference, what do you do? Finally, during inference, okay, you take x cap coming from PT, okay, and then pass it through phi star, which will give you ZT, then take ZT, okay, and pass it through the classifier. This will give you the labels, which are the predicted labels on DT. Does it make sense? So this is how you are doing. So what you are doing is you are training a classifier on source data, okay, using features that have the same distribution as that of the target data. Now you are training a classifier that has exactly that is working on a feature space whose distribution follows exactly that of the features of the target, and you are ensuring that it will happen. You're enforcing that it will happen via adversarial training. Okay. So now once it is done, the features that are extracted for the source data is same as the features for the target data. So now if you take the features for the target data and pass it through the classifier that is trained on source features, it is expected to do well on the features of the target data, because you have ensured via adversarial training that the features, the distribution of the features of the source data is same as the distribution of the features of the target data. This thing is called domain adversarial training, and it is shown to be a very effective method in reducing the problems with unsupervised domain adaptation. Okay, any questions on this method? Yeah, Lukesh.
Sir, is it necessary to backpropagate through phi from h of theta as well?
Yes, because otherwise what will happen, no? The features that have been learned, okay, may not be such that they are conducive for classification. So you'll have to ensure that the classification also happens. The classification on the source data has to happen.
Can't that be captured by h of theta itself?
H of theta is trained, no? You have to train h of theta.
Yeah. So during that training, won't that
No, wasn't it your question? You are saying just use the ZS and train h of theta separately is what you are saying, is it?
Right.
Why do you have to train phi together with h of theta? Is that your question?
Right.
See, if you take ZS separately and train h of theta, what will happen is the features that have been learned to ensure that these two distributions are same may not be useful for the classification. For instance, what can happen is, suppose both of them for all x, right, or both of the PZS and PZT are such that they give you one vector for all data points. Let's say that they all collapse. Okay, so if that happens, even then the distribution matches. PCS and PCT matches if for all x it will give you one vector, but that is not useful for classification. Understood? So the
Yeah,
features that
got
have
it.
been learned have to be such that they are useful for classification, and that's why you have the classification objective also together while you are training it.
Okay, sir. Got it. Thank you.
Okay, Sanchit?
Sir, can you please explain once again this process, like how we are training and like how we are doing these, like taking the supervised classification and the
Okay.
discriminator part, backpropagation together?
See, first you take the source data, pass it through this phi network, you get a feature ZS, right? And then you take XCAP, pass it through that network. I mean, you initialize this phi network randomly, you get ZT. Okay. Now ZS becomes your true data, and ZT becomes your generated data, and use those with a discriminator to adversarially backpropagate phi Z through the phi X network, and ensure that the distribution of ZS and ZT are the same. This is the usual GAN training.
Okay.
The only difference between a usual GAN training and this is that in a usual GAN, right, the real data is not passed through the network, right, generator network. You assume that it's already there with you. But here, GS becomes your real data and GT becomes your generated data. I use that with a discriminator to ensure that the distributions are same. That is GAN training. Okay. Then you have another classifier which is trained together with the GAN, where this classifier takes data from the source features and predicts the source labels and train it in a supervised way. Now this phi network, which is the feature extractor, will be trained both using the adversarial objective and the supervised objective together, so that it has to ensure that the distributions of source and target data matches, while the classification also happens properly.
So, sir, these X and X cap, these are from the available input.
See, I have defined it already. I mean, you should not forget. See, this is ds and dt are given. So X is the samples from ds and X cap are samples from dt. They're given.
Okay.
That is what is given, no?
Okay, sir.
Okay. Raghavendra?
Yes, sir. I mean, we have this label data here, right? So what
Label
advantage
data
do we
only
correct
label
for the
data
source?
only from the source, correct?
Yes. So I mean, what advantage this generative model here? I mean, adds to this supervised learning, because we could also directly train the H network over the
But
XS
why
itself.
would what? Yeah, if you do that, then what is the guarantee that the X? If you suppose you train a classifier on X and pass X cap through it, it will have a very bad performance because
Why is that so?
because PS and PT are not the same. No, distributions and PS and PT are not the same. That's why I showed you that that picture, right, where you had the MNIST and the SVHN data, right? The distribution of PS and PT are not the same. I should maybe write it explicitly. See here, PS.
But they must be close enough, right?
They will not be. That is the problem with domain adaptation. When the IID assumption breaks, right? When the resource data is not equal to the target data, the classifier trained on one will fail miserably on the other. Actually, you can, yeah.
So if you go back to the diagram, right? So does it mean that the phi network is actually extracting features which are common across distribution? Is that how we can see it?
It is ensuring that the features are extracted in such a way that across both the distributions the features have features are same.
Overlap.
See, while PT, right? PT is, or rather,
okay.
Well, PS is not equal to PT, right? PZS is equal to PCT by construction. That is the point.
And that's what we are trying to identify, which is the distribution which is overlapping between those two.
We're not identifying that way. So not that we should not say that there exists a distribution that overlaps. We are trying to enforce features such a way that for both the distributions they match.
Okay. Yeah. Understood. Thank you.
Okay. Anything else? Also called DAN. Okay. Domain adversarial networks, or DAN. Very powerful technique, and it has see, actually I wanted to include this as a part of assignment, but I thought it'll be too much. So if anyone is interested, you can try that out. Take MNIST and the UPS data set. Examples also here. This can be MNIST. This can be UPS data. You train a classifier on MNIST and test it using UPS data set, you will see a drastic reduction in accuracy. Okay. Now, and then you do this domain adversarial networks and see the accuracy on the target data will increase considerably. Okay, so that's about it. Yeah, see, the last thing with GANs is time is too short and we have so many things to discuss. It's supposed to be a content for at least 2 courses, if not more. Okay, so the last thing that I'll talk about for GANs in GANs is this thing called the Wasserstein's GANs. Okay, this is needed only for that FID thing. Otherwise, we could have skipped it. Okay, we'll do it. Okay. Wasserstein's GAN, or optimal transport. WGANs. Okay. Okay, so now you know that for the F divergence minimizers, right, are very unstable in practice. So you have already seen that, right? The GAN training is very difficult. Training GAN is very difficult because, so this is something that you have seen, right? GAN training is very difficult because of that saddle point problem that is there. Okay, that is one problem. The question is, what makes GAN training hard? Okay. So in this paper, which is called Wasserstein GAN, what they show is the following. Suppose so you have what is the notation that we are using for that? P x and p theta, right? Suppose px and p theta, okay, are such that their supports, okay, don't overlap. Now I will explain what this means. See, px and p theta, okay, first of all, px and p theta, okay, are distributions over X, right? Which is typically some d-dimensional real space, correct? This is how it is. Now, typically, okay, distributions over real data, okay, real data lies over a small subspace also called as manifold in the ambient space RD. I'll explain what this means, okay? Hold on. Okay. Here is what I mean. Suppose you are generating or rather generating data like this. Let's say that I toss a coin, okay, and then if it's head, I will fill this pixel with 1. If it's tail, I will fill that pixel with 0. Do you understand what I'm doing? I'm tossing a coin, okay, and depending upon the outcome of that coin, I will decide to fill this particular pixel. Let's say that I have a grid of, let's say, 24 by 24 or 28 by 28. I think MNIST is 28 by 28. Now I'll fill these pixels, 784 pixels like this. I toss a coin. If it's head, I will fill that pixel with 1. If it's tail, I will fill that pixel with 0. Okay. Now the question is, what is the probability or likelihood that this procedure will generate MNIST dataset? Do you see the question? Do you understand the question? Okay. So now can somebody tell me what is the probability of generating MNIST via this procedure?
Should be very low.
Yeah, it's really extremely low, right? There's actually called the typewriter monkey problem, right? Where they say that you make a monkey sit on a typewriter and start typing randomly. Now, what is the likelihood that it will create Hamlet, right, or Shakespeare's work? That is the question. Say that it's very, very low, right? I mean, similarly, getting a data set which is semantically meaningful like MNIST by doing this procedure, random procedure, is very, very low. Now, this means that out of all possible images, binary images, MNIST occupies a very, very small space in 784 dimensional space. Do you see that? See, this example was to show that out of all possible points in 784 dimensional space, MNIST occupies a tiny region. That is what I have written here, right? The distributions over real data lies on a very small subspace or manifold in the ambient space RD. Does it make sense? So now what is the consequence of this? The consequence of this is, this implies that there's a high chance that supports meaning the points where the distributions are non-zero, okay? That supports of px and p theta are not like x and p theta are not perfectly aligned. Right, because we are talking about of two distributions, right, in RD, and we know that the distributions of images are actually supported on a very tiny space in RD. So if I take two distributions that are in RD, then their supports will not be perfectly aligned. Okay, there is a high chance of them being not perfectly aligned. Correct? Now again, what is the consequence of this? This is, it can be shown that that one can always find a perfect discriminator okay, which is that a DW network with 100% accuracy when the supports of p theta and px are not the same. Right? So this is saying that, okay, now if the supports of px and p theta, they do not align perfectly or are not exactly the same, then you can always find a discriminator with 100% accuracy. Okay. Now, if you find a discriminator with 100% accuracy, what does this imply? This implies that the GAN training saturates. The moment you find a discriminator with 100% accuracy, there is no signal to the generator to learn, isn't it? Because it is perfectly classifying. That's all, you are done. Right? So GAN training simply saturates. And this is the reason, okay, why GAN training becomes difficult. So let me tell you what I said. See, the argument that is given is, first thing is that the data that is lying, I mean, that occurs naturally, like images and text and all that, they occupy a tiny manifold or tiny little space in the ambient space. Okay. Now this means that the true data and the generated data, okay, they both lie on tiny manifolds, and those tiny manifolds may not perfectly align. Okay. Now, if they do not perfectly align, I mean, even if there is a single point where there is misalignment, then it can be shown that in such cases, you can always find a discriminator that is perfect. Now, once you find a perfect discriminator, okay, then the GAN training simply saturates. So this can also be said in a different way, saying that this means that for px and p theta with misaligned supports, misaligned supports okay. If you take any F divergence, okay, this will be either infinity or some constant. Let me say it's a constant. Simply become a constant. Now what if it becomes constant? This will become independent of theta. If it becomes independent of theta, then that's all right. I mean, GAN training simply saturates because the divergence you're calculating is independent of theta, and there is no way that you can learn more. Okay, this is why mode collapse also happens. This happens all the time. So the respite or solution for this is use a softer metric. Softer divergence metric. Okay, that quantifies how close the manifolds are, called support manifolds are. Supports of, we are talking about px and p theta. Okay, instead of just measuring if they overlap or not. They're perfectly aligned or not. Okay. This is demotivation. So what we are saying is that if the manifolds do not perfectly align, okay, then all the F divergences that we saw simply will max out, or rather become a constant, which will become independent of theta, and that's why GAN training saturates. So instead of that, it's better to have another metric, a divergence metric, that will tell you how close or far the manifolds on which distributions are supported are, instead of just making it a constant. In fact, whenever the manifolds do not align, you want that metric that you are thinking of to just measure how far or close the manifolds are without just maxing out or becoming a constant. So if this happens, right, what we are saying is that you can't find a perfect discriminator, and that is why the GAN training does not saturate. Okay, so we will see. I mean, this metric happens to be, that metric is what is called as the Wasserstein metric. Also called as the optimal transport. Which I'll define in a while. Yeah, before we go to the definitions, I'll take questions on the discussion so far. Any questions? Yeah, Sanchit?
Sir, what do we mean by the support here?
If you take a distribution, supports are the points on which distribution is non-zero.
So like,
Write that. If you take a uniform distribution between, let's say, A and B, support of distribution is set AB, on which the distribution is non-zero. Is it all right? So Gaussian distribution, right, will have infinite support, for instance. It's a set, okay? It's a set over which the data has been observed.
okay.
Okay, any other question? Yeah, Raghavendra.
Yeah, so here we are only trying to say that if the supports match, then they are close enough. So we are not really looking at the divergence metric in addition.
No, in F divergence, we do compare distributions. Okay, I mean, we saw that, right? We actually compare distributions. Okay, but the thing is, if the distributions, if the distribution that we are comparing will have a mismatch, okay, in terms of non-alignment, then what this paper says is that you can always find a perfect discriminator, and that's why training becomes unstable. Okay, so you basically, the motivation is that you need another alternative metric, okay, that is not over dependent on alignment of the supports of these distributions. Okay.
So I mean, it's in addition to the divergence minimization, or this is a separate way to optimize.
You minimize the divergence only. Basically, you minimize the divergence, but the divergence metric that you are coming up with is not sensitive to misalignment between supports. That's all.
Okay.
Okay. So Wasserstein's metric is also a divergence minimization metric only. So given two distributions, Px and P theta, the Wasserstein's metric between them is defined as follows. Keeping some details here because we don't have a lot of time. So this is metric is given as the minimum of the expectation of the two norm, and this expectation is over x and x cap. They come from some new, and this minimization is over all new, okay, which belongs to a joint distribution between Px and P. I will explain all this. Give me a minute. Write that down and then explain. This is the definition of the Wasserstein's distance. Okay, I'll tell you what this means. Now, suppose there are two discrete distributions. Okay, I'll do it in one dimensions to ensure that the idea is clear. So let's say that this is x. There is another distribution, which is a histogram. The x cap. Let's say that this is px and this is px cap or p theta. Okay. Now the mass in px can be redistributed such that it transforms to p theta. Do you agree? The mass in px can be redistributed, okay, such that it will transform to morph into p theta. Do you agree? How do we do that? So it's like this. How do we do that? We take, let's say that this is x1 and this is some xk. You take some mass from x1 and reduce it and put it to x2 and so on, right? I mean, you can redistribute the mass in px so that it will get transformed to p theta, isn't it? Do you agree?
Sir, but usually we are not supposed to touch x, right? So it's like a source distribution.
Is what? No. See, forget about source and target and all that. No, I'm just simply saying, given two distributions, you can always change the distribute mass in one distribution to get it morphed into some other distribution. Correct?
Correct.
Now the thing is, now this redistribution can be expressed as a table. Let's say that this has k and this is x cap 1 to x cap L. Okay. Now I will write a table. Okay. So in this direction, this is x cap. And in this direction, it is x. Now this is x1 through xk, and this is x1 cap through xl. Right? So what I'm saying is, how much mass should I take from x1 and how should I put it in, let's say here. So let's say that I put the 0.3% of x1 here and I put 0.2% of it and I'll write 0.01% of x1 here and then redistribute amongst all x1 cap through xl. Same thing with x2 also, right? I take 0.1% and 0.4% and 0.02% and so on. Do you see that? So what I'm saying is every row here is telling me how much mass, how should I redistribute 1xk, okay, amongst all possible x caps such that it will get transformed to p theta. Do you agree? And every row should sum to 1, right? Because you can, the total mass on x1 should sum to 1, correct? So now this, right? What is this? If you closely look at it, is actually a joint distribution. Joint distribution between px and p theta. Shall I call it as px cap? It's okay. You understand, no? X cap is coming from p theta. Is this okay? Px is sampled from px is sampled from px here and x cap is sampled from p theta. So this table, okay, which will tell you how to redistribute x to px to get morphed into p theta is actually a joint distribution between px and p theta. Agreed? Any questions so far? Yeah, Abhitosh, write this down.
Shouldn't it be the reverse, that you are trying to adjust p theta so that it becomes equivalent to px, or is it because you do not know?
No. It's no. See, again, I'm telling, forget about it for a while. No, you forget what is p theta, what is px. There's two distributions. Of course, you can write it that way, right? I mean, you say that p theta is being adjusted in GAN framework. That is what you're trying to say, right?
Yeah.
But in general, it doesn't matter. No, in general, I'm defining divergence metric between two distributions. Can mean anything.
Okay.
That is why if it's confusing for you, let me change it. There is no find and replace here, so you have to do it manually.
Yeah.
Any other questions on this? So a joint distribution between px and p theta, px cap now, px cap, okay, specifies a transport plan. Okay, it's called a transport plan. Transport plan, okay, between px and px cap. So now if you give me a joint distribution between px and px cap, I'm simply saying every joint distribution is telling me how to convert or redistribute masses in px such that it gets mapped to px cap. Do you agree? Now, suppose, okay, suppose now I move, suppose a mass x cap, okay, is, or rather x is moved to x cap, right? Then norm between x and x cap gives you the distance of movement. Okay, and if you evaluate the joint distribution at these points x and x cap, give you the mass that was moved. Right, this much of mass was moved, this much of distance. So now px x cap, which is the joint distribution between these two, if you multiply this with this thing, so what is distance times mass? It's the work done, right, in moving the mass by a distance of x minus x cap. Correct? The mass into distance is the work done, right, by definition. Now, if I integrate this, okay, over the entire joint distribution, what will this give me? This is by definition the expectation of, okay, over the joint distribution of px x cap. What is this? This is the average work done, okay, in a transport plan. Specified by Do you agree? Now, every joint distribution between x and x cap will give me a transport plan, right? Which would tell me how to transform one distribution to the other, correct? Now, if I multiply, right, if I take the expected value of the distance between the supports, okay, over the joint distribution, it will tell me the average work done in a transport plan that is specified by the joint distribution. Everybody agree on this? Hello? Am I audible? Hello?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, is this clear? Okay. Now, the question that I'm asking is, given multiple transport plans that are possible, every transport plan is a joint distribution, mind you, right? Joint distributions, okay, possible. Between two random variables x and x cap, okay? Now, which one has the least work done? In other words, what is the least work done, okay, to transform px to px cap? How do you specify this? So now what you do is that if you take a joint distribution nu, okay, which is a joint distribution between x and x cap, okay, this will give you the work done via that joint distribution. Now, amongst all possible transport plans or the joint distribution that will take px to p cap, give me the one, okay. So here phi, okay, represents set of all possible joint distributions between x and x cap. All possible joint distributions or transport plans, right? Because every joint distribution is a transport plan between x and x cap. Now this is seeking, what is this seeking? This is seeking the least, or rather the transport plan with the least average work. Do you see this? So I'm saying amongst all possible joint distributions or amongst all possible ways that I can transform my px to px cap, give me the one, right, that corresponds to the least work done. Do you agree? Do you see this? Now, this is what is called as the Wasserstein's distance. Wasserstein's distance between two distributions px and px cap is the minimum, okay? And please note the minimization is over. Minimization is over all possible transport plans, okay? That would transform px to px cap. Now the question that I'm asking is, amongst, so nu is a joint distribution between, nu belongs to set pi, okay, is a joint distribution between x and x cap. Now, amongst all possible joint distributions that would transform px to px cap, give me the one that has the least work done. So that is the Wasserstein's distance. Now you can see that lesser the Wasserstein's distance, okay, closer are px and p cap, isn't it? Because if px and px cap are close, okay, then the amount of work that you should do to bring px to px cap will be least. Now there can be other transport plans that would, I mean, even if px and px cap are close, there can exist transport plans, right, that would have a that would involve a lot of work. But since we are seeking the minimum work done to transform px to px cap, if they are close enough, then you don't have to do a lot of work to transform px to px cap. That's why it's a distance metric between two distributions. So this is also called, that's why it's also called optimal transport. Wasserstein's metric is also called as optimal transport. Any questions on the definition? This is hello? Is there any question?
Not now.
Am I audible?
Yes.
Yes, sir. Yes, sir. Yeah.
Okay, great. Okay, so now this is shown to be a softer metric, right? So Wasserstein's distance is a softer metric, okay, compared to F divergence. So in the sense that it will not max out, right, or saturate. With misalignment. Okay, this is the misalignment of the supports. So this is the greatest thing, right? I mean, that you can use the Wasserstein's metric to, I mean, it will become much stabler if you use Wasserstein's metric. Now, how is this related to adversarial learning? Is that so? The next question is, I'll continue the class till 11:15, right? And then we will take a 10 minutes break. Okay, let's finish this. The question is how to build a generative model that optimizes the Wasserstein's metric. Okay, this is a good metric, fine. Now, how do we build a generative model that would optimizes the Wasserstein's metric? Okay, so thankfully there exists this duality, okay, which is called the Kontrovich-Rubinstein's duality. That says that Wasserstein's distance between two distributions, Px and P theta, okay, can be expressed as a maximum, okay, over set of functions. Let's call them as TW. Which are like this. I'll tell you what this is. So this is an expectation x coming from Px, simply TW of x, minus expectation of x cap coming from P theta to have again TW of x. Right? So now you know, right? I mean, this, so now if you want to minimize P theta, is simply you have a min over theta, and Wasserstein's distance is simply a max over this TW. I'll tell you what this norm of TW less than this means. And you have this usual cost, right, which we know how to approximate using sample estimates. X cap, sorry, this is X cap. Cap from P theta. right? So now this, what is this? Again, this became a adversarial optimization. Okay, how do you optimize this? Same thing, you have a generator network, which will take a Z and gives you X cap coming from P theta, the usual story, and you have this critique network here, PW of X, right? So your real number in this case, and this is either X or you have X cap that goes as input, because you have to compute the expectation over both of that, right? And then the only constraint is that the T network, right, have to be 1 Lipschitz. So what is meant by that, I will just tell you. Implies that if you take TW of x1 minus TW of x2 divided by x1 minus x2, this is upper bounded by 1. This is the definition of 1 Lipschitz. So if you look at it, it is exactly a GAN, right? Optimizing the Wasserstein's distance is exactly a GAN. That's why it's called a WGAN. The only thing is the discriminator network, right, or the critique network have to be 1 Lipschitz. Of course, the form of the loss function changes a little, because there you have the expectation of f star of TW. Here you don't have that f function, right? Otherwise, it is simply an adversarial optimization problem that you are solving, right? But with only one additional constraint, that the discriminator network have to have bounded derivatives, right? Or it should be 1 Lipschitz. Now, how do you make a neural network 1 Lipschitz is a question that I'll answer in a while. But yeah, so but for that, it is simply again with the objective function taking expectations over two distributions, and then you optimize. The advantage is in a GAN, right? What happens is, or an F divergence minimizer, this maximization that you are constructing, no, is actually a lower bound on the divergence. But here there is an equality. You see, the Wasserstein's metric is exactly equal to this maximization problem, which is again, no, that's what makes it a softer metric. Now, the practical implication of this is, whenever you are implementing a GAN, right, always implement a WGAN, because it is much more stabler in terms of training. Okay, even for your assignment, no, question 1 and 2, I would recommend that you implement a WGAN. So now, how does it change? The only thing that it changes, this will not be between 0 and 1 now. It will simply, you will have a linear activation at the output. Linear activation, okay? The loss function will not have a log of d of g or something. It will simply have the output of this. It will be expectation of the output of this. So this will be this is the output of this network, okay? That's one thing. The other thing is, you'll have to ensure that the discriminator network is Lipschitz. So now, to practically, what you do is that you normalize the weights of TW, okay, such that their norm is always 1. If you do this, then it will become 1 Lipschitz. So what you should do is, after every gradient step, right? After every gradient step, every gradient update. So after every gradient update, what you do is take the weights update, take the weights of the discriminator network and normalize them so that they will have unit norm. If you do that, it will become 1 Lipschitz. That's all. That is the only thing that you should do while you are training the Wasserstein GAN. And this is shown to be much more stabler for training, and it will give you much better like outcomes compared to F divergence minimization, even though this also happens to be a saddle point on adversarial optimization. Okay, with the only constraint that you should have the discriminator to be 1 Lipschitz. Okay, that's about WGANs. Any questions on this? Yes, go on, Raghavendra.
Yeah, so the norm that we are talking about here is the L2 norm, or
where here? Yeah,
this,
this is L2. This is L2. This is L2. Yeah. It's good that you asked that question, right? Here, when we define the Wasserstein's metric, it's always 2 that we talk about here, right? The 2 norm between x and x cap. Okay. And this duality, the control which Rubinstein's duality is called Wasserstein's 2. In general, you can use a pth norm here. If you do 1 norm here, that will become Wasserstein's 1. If you use 2 norm, it will become Wasserstein's 2. If you use p norm, it will become p Wasserstein's distance in general. But generally, Wasserstein's 2 is what is used everywhere. And the duality rate or the GAN formulation comes up for Wasserstein's 2. That all right?
Okay, so the duality applies only to Wasserstein's
the Wasserstein's 2. Yeah. Yeah, Sarvesh?
Just for calculating the norm of the network, you just have to put all the weights in a vector in any order and then just calculate the norm. Right?
Yeah. Simply vectorize it, compute the norm and divide it by the norm of it. You don't have to compute it. No, just divide the weights, every individual weight with its norm.
Okay. Yeah, and it works for every network and convolution also same thing.
Yeah, same thing. Yeah.
Thank you.
Okay, nothing else, right? I mean, whenever you implement a GAN, always implement a WGAN, much more stabler. Okay. The final piece before we close GAN is like, how do you evaluate generative or evaluate GANs, right? Typically, this is I should not be calling it as GANs. You can do it for any generative model. Now, given x1 through xn, sample from some distribution px, typically the real data, and you have one cap through xn cap. This is sampled from p theta star. This is like the generated data post training, of course, right? Okay. Now the goal compare the closeness. Let's call this as T real and T generated. Okay. Compare DR and DG. Now, how do you compare these two? You need a metric, no, to compare these two. Of course, now you need to resort to some distributional divergence metric only, no, to compare DR and D2. What is done is typically there are multiple metrics to do it. One of the famous metrics is what is called as the Fréchet's inception distance. It's called abbreviated as FID. Might have seen, no, FID is the metric that is used to evaluate the quality of generated data. So what is this? At the heart of it, FID is simply Wasserstein's metric. Okay. Simply Wasserstein's metric between like px cap and p theta cap, but it is done in a convoluted way. I'll tell you what is done. So what is done in FID is that first step is take samples of dr and dg. Okay. Now pass them through an inception network, a pre-trained inception through an inception net. That's why the name inception distance. Okay. Inception network pre-trained on ImageNet. Okay. Now then take the features from some nth layer. Some different people take it different layers. I think example is 64th layer. Okay. Now what was done so far is that you have a pre-trained inception network. Okay. Now you pass your X and X caps both through this and take the features at some 64th layer, right? This is, you call this as Z real and Z generated. Okay. Then now you will have two data sets, right? Let's call that as D cap real, which is Z real 1, Z real 2, up to Z real n. And you have D generated cap, which is Z generated 1, Z generated 2, and Z generated n. So here ZRI is, let's call this as some phi. Okay. So now phi at 64th layer of ZI, Xi, and ZGI is phi at 64 of X cap I. Okay. Where phi is the pre-trained inception net. Okay. So far, so good. Any questions on this? Given data, real data and generated data, take a pre-trained inception network. Okay. Pass both of them through that and take the 64th layer features of both of them and collect them as vectors. You get two sets. Is this okay so far? Okay. Now what you do is, this is the third step. The fourth step is that compute mean and variance, okay, for dr cap and dg cap. Let's call this as mu real, okay, and sigma real. Compute mu real on z real. You compute sigma real on z real. You compute mu generated on z generated. Compute sigma generated on sigma generated. Is that okay? Now the fifth step is that assume okay, z real and z generated both to be coming from Gaussian distributions. So now z real comes from Gaussian with mu real and sigma real, and zg comes from a Gaussian from mu g and sigma g. Okay. Then finally you compute the Wasserstein's metric between the normal distribution at mu real, sigma real, And so this is FID. Is this clear how to do it? Now I'll tell you, this actually is given by a formula. Wasserstein's distance between two Gaussian distributions is given by the simple formula real minus mu g from 2 squared plus the trace of sigma real plus sigma generated dash minus 2 sigma real sigma generated dash to the power of half. See, this is a scalar because it's a norm. Okay, and this is a trace. No, trace of a matrix is also a scalar. Okay, and therefore this is the FID, which will be a scalar. So this Wasserstein's 2 metric, no, scalar. So this is lower the better. Two distributions match, then it will be 0 because it is Wasserstein's distance between two Gaussian distribution. Lower the better, not between. That's it. Let me show you the entire procedure. Have a look at it, okay? And let me know if you have questions on FID. So this is the metric that is used to, one of the metrics that is used to quantify the goodness of generated data, be it from GANs or VAEs or anything, you can compute FID. So what is FID? Let me quickly go through the steps now. Now you have samples from the generated and the real data, pass it through a pre-trained inception network to get the features. I mean, I'm not sure if it's 64th layer or something. Different people use different layers anyway. Okay. So now once you get those features, assume that those features follow Gaussian distribution and compute the mean and variances of them, and use those mean and variances to compute the Wasserstein's 2 metric between these two features of real data and generated data using this formula. That is your FID. Any questions on the computation of FID? I've asked you to compute FID, right, on the data that you generate using GANs. So this is the formula that you should implement. There are standard implementations of FID as well. Yeah, but this is what they do. Okay, Sarvesh.
Sir, what is sigma g prime?
Oh, sorry, the sigma g only. Yeah. Okay. Yeah, Vivek.
So I have two questions. One is why did you place so much of importance on one particular inception architecture?
I didn't. I mean, somebody did, because if you read the FID paper, what they say is inception architecture correlates well with human perception is what they have done by doing some perception studies.
Okay. Okay. Second question is, suppose I am modifying the problem a little bit and I ask like I want to see the inception, I mean the distance between generated images of a given style. Like if I'm not going to focus on content at all and I just want to focus on style, so can I modify the picking up the 64th layer feature vectors and instead replace them with maybe the gram matrix or the ADA in layer activations, I mean, and continue with the same procedure? Will I get a meaningful result?
It is not FID, but yeah, so it is something, right? I mean, you might get some meaningful result, but it's not FID by definition. That's all. You can't say that it's the standard FID metric. Okay. But
Okay,
yeah,
it is
that
like
does make sense.
okay, fine. I mean, the actual problem is I want to recommend images to
Vivek, yeah, I
okay,
understand.
yeah.
Shall we take it offline, because
Yes.
it may not be relevant to the class. Okay. Please ping me, we can discuss over that. Okay, any other question on FID? Okay, so this is the end of GANs for this course. I mean, there are too many things that are there. Yeah, this is the end of generative adversarial networks. Let's move on to VAEs. Yeah, so okay, so we come to the end of GANs then. So let's move on to the next topic, which is variational autoencoders. Shall we take a break? Okay, so how long? It's 11:18. Shall we come back at yeah, Sandeep? I think yeah. So we'll come back at 11:35 and go up to 12:20 perhaps, and then we'll stop. 11:35. Okay, yeah, 15 minutes. Okay, see you now. Bye. Bye. Hello, shall we resume?
Yes, sir.
Okay. Okay. The next class of generative models that we would consider are these variational autoencoders or VAEs. Okay. Now, these come under a broad family of models called latent variable models. Okay, latent variable models. So what do you mean by a latent variable model is that you have theta, P is what our starting point is, right? On as usual IID from an unknown distribution Px. Okay. Now, if suppose P theta of x denotes a model, what is a model? Model is basically a distribution over theta, right? Suppose P theta denotes a model. Okay. A latent variable model is the following. It's defined as follows. P theta of x is given as a marginal over the joint distribution of the data and another variable z, okay, where z is another is let's say is a hidden. That's why the name latent variable. Okay, hidden or unobserved random variable. Or this is integral if it's continuous. Okay, if z is discrete, hold on. I wanted to move that anyway. I actually wanted. Let's do that. Okay. So this if z is discrete, this z is continuous. Okay. Now where z is a hidden or unobserved random variable. Okay. So this is the definition of a latent variable model where you express your data, okay, in terms of a marginal, okay, over the joint distribution between the data and one other unobserved random variable. Okay, so typically, give you examples of what this. So typically z is also estimated or learned along with the model parameters theta. Okay, so basically what we are saying is for each xi in data, okay, there exists a zi, okay, corresponding to xi. Xi that is unobserved. Okay, now this zi examples for this where z is discrete. Okay, let's say that z is discrete and it will take, let's say, 1 to 0 to like m values, let's say 1 to m values. Values, then given an xi belonging to D, okay, zi given this xi, okay, may indicate indicates say that, let's say zi comma xi clusters xi into one of m categories. You understand? So in this sense, right, a Gaussian mixture model of which the k-means clustering is a special case, okay, are both latent variable models. Any questions on this? So basically what we are saying is the following, right? Given data, what we do is that we model our data this way, which is a marginal over the joint distribution of the data and another random variable called z. Okay. Now what is this z? This z is a latent variable or an unobserved random variable that is not with data, that is not actually measured or seen with the data, but it is there with the data. Okay. Now, what is the advantage of having this sort of a modeling is there are multiple reasons. One, having a latent variable model will enable will enable model learning. Okay, easier, make it easier. In the case of Gaussian mixture model, it will make it easier, algebraically easier. That is one reason. The other reason is if you have a latent variable model, you can actually get information like this, which is given a particular xi after training, right? If you estimate the corresponding latent variable, it will tell you if it's discrete, it will tell you what cluster every xi belongs to. So that is the classical example of k-means clustering and Gaussian GMM clustering, where they are both latent variable models, which will tell you for every xi, it will tell you what cluster xi belongs to. The second example can be, okay, the first example. Second example is where Z is continuous, which is actually an autoencoder or a VAE also, where Zi given an Xi, okay, can be seen as your Z, then some RK, it's a continuous vector, can be seen as feature corresponding to Xi. So latent variable models, right, will enable feature extraction. You can use Zi rather than Xi, okay, for downstream tasks and all that. So these are called, I mean, these are feature extractors. So that's why you want to model the data Xi by introducing one other random variable Zi, which is called the latent variable. Any questions on this motivation?
Sir, for the continuous case, we are saying that Zi by Xi can be seen as a feature for
not by Zi given Xi. It's a conditional random variable, conditional distribution.
okay.
Zi
So this
given Xi.
sorry for that. Zi given Xi can be seen as a feature corresponding to Zi.
Corresponding to Xi.
Okay. Okay, sir.
So the feature should be useful in some way, right?
Correct. It will be useful in some way. That's the point. Latent variable models are imposed because features are useful in some way. Now that's what I'm saying. So now the literature, right? These latent variable models are designed in such a way that you learn the latent variable and the model parameters together. All right. Not only in GANs, right? What did we learn? We basically learned the model. Okay, but in latent variable models, learn the model. Okay, but you will also learn the latent variable together. That all right? Okay, shall we move on? Okay. Now let's look at can't I draw straight lines here in this thing? Is there a way to do it? A long press in GoodNotes, right? A long press would make it a straight line. Here I don't know how. I mean, I have to go insert line and all that. That's too much.
No, sir, there is in the draw itself. In the draw itself. Yeah. These symbols are there. After pencils, there are one round and one square. That is giving you yes.
Every time I'll have to do this, huh? Okay, fine.
So I guess, sir, next to that menu also, like that, if you draw a square, it will convert to square. Yeah, this one.
Okay.
Yeah, but sir, when you type, it will convert your character as well. It will disturb you.
Okay, so this will convert into regular figures, huh? No. Okay, let's not complicate stuff. Maybe I will use a line and do it. Okay, fine. So now modeling. Yeah, latent variable models. Okay, so recall. So suppose p theta x. Yes, I'll for now use assume that the latent variables are continuous, and this is my model. Denote latent variable model. Okay. Now again the same thing, right? So goal given D that are samples, IID samples from PX. I need to estimate E theta, okay, such that some divergence metric for VAE, right? The divergence metric that is taken as the KL, okay, minimized. Okay, this is our goal. Okay, so we need theta star, that's the minimizer of E KL between X and E theta. Recall that this is equal to maximizer of the expected log likelihood. Do you remember this? We had done this, right? Does all of you remember this?
Minimizing KL divergence is same as maximizing log likelihood.
Correct. Yeah, expected log likelihood, right? Maximize the log likelihood. Okay, this is what it is. So let's write that we are interested in maximizing the likelihood function. So I'll remove the expectation because if you maximize the likelihood for all x, the expectation will also be maximized, right? So that's because just to make the algebra easier, I mean, the final loss function and everything will have an outer expectation with respect to px, which will have a sum over all samples in px. Okay, let us remove that to make life a little easier. So our objective is to maximize the log of the likelihood under the model p theta. Okay, so denote log p theta of x by L theta. Let's call that L theta. Now our objective is to maximize L theta. Okay. Now how do we do that? Under a latent variable model, we have L theta is now equal to log p theta of x. Now under the latent variable model, this is integral p theta x please let me know if any one of these steps are not clear to you. Okay. Okay, this is because in latent variable models, my p theta is the marginal over these two, right? That is why it is equal to this. Okay, now this is equal to log of e theta x and c times q z given x divided by q c given x c where so it here so that I can continue. Q of z given x is some distribution over z. So Q of z given x is some distribution over the latent variable, right? You take any distribution over latent variable, right? You can just multiply and divide by that, okay? And the integral doesn't change. Is this all right? Q is some distribution over the latent variable. Is this okay? It can be any arbitrary distribution, doesn't matter. Okay. Now this is log of expectation of d theta c divided by q c given x with respect to q. Is that all right? By definition, see what have I done? Just group this together. Okay. And taken this as a function and written that integral as the expectation over z. Is that okay? Okay. Now there's something called Jensen's inequality. That says that log of expectation is always less than or equal to expectation of log of that function. Has everybody heard of Jensen's inequality or not?
Yes, sir.
If not, right, maybe we can take it in the TA session. Okay, just look into it, no? So using that, what we can do is, so we have now L theta, which is our log likelihood that we would want to maximize, is equal to log of expectation of this entire thing with respect to Q. Now I can write that as something that is less than or equal to, greater than or equal to, because this is equal to greater than or equal to the expectation of log of that function.
Sir, less than equal to, based on the previous expression.
See, log is less than or equal to that expectation of log.
Yes, sir.
So this is log. So this is less than, that is less than expectation of log, correct? No, log is less than expectation of log. Should be correct, no?
No, sir.
See, other way around.
It should be other way around.
Okay, so then this is this. I think that it's correct now, right?
No, sir, I don't remember the inequality sign correctly.
No, that's okay. But with this inequality, whatever I have written is correct, no? See,
yes,
I know for a fact that this is right. So we'll have to change the Jensen's inequality correspondingly.
Okay, sir.
See, Jensen's inequality becomes an upper bound or a lower bound depending upon this function. If this function is concave, then it is 1. It is convex, it is something else. So sometimes I get confused about it. This is correct, right? So just tell me that if it's greater than or equal to here, this will become greater than or equal to here, correct?
Yes, sir.
So then distance inequality is correct. Okay. Right. So now this is greater than or equal to what do we have here? It's an integral for c. We have q of c given x, okay, times log of p theta of x given c divided by rho c given x dz. Okay. Okay. Now this, let this entire thing, right? Note that this is a function of two things, right? It's a function of theta, obviously. It's also a function of q distribution that we have chosen, isn't it? Depending upon what q we choose here when we started, right? There is some distribution over z. So you will get a different lower bound on the likelihood, correct? Now this implies, what did we do so far is that by introducing a latent variable model and a distribution over it, we showed that the function, which is the log likelihood that we would want to maximize, is lower bounded by some function, which is a function of the model parameters and a distribution over latent variable. Okay. So now this q, which is a distribution, conditional distribution over z, is referred to as the variational posterior, variational latent posterior. That's why the name VAE. Okay. What is that? It's a distribution over z. Okay. And this f theta is also called as the evidence lower bound. It's a lower bound, okay, on log likelihood. Okay. Log likelihood is also called as evidence. When it's another name for that, no? So you want to, in all models, you want to maximize the evidence under the model P theta. So now you have constructed a lower bound on the evidence, okay, based on a variation latent posterior, and this is abbreviated as elbow. Is this clear? Now, what we need is we need to remember that we wanted to find a theta that would maximize the evidence or the log likelihood. Okay. Now, this is equivalently maximizing the lower bound on the evidence, because in latent variable models, maximizing the evidence will become difficult, just like we did it with the F divergence, right? Minimizing the F divergence directly was not feasible. We constructed a lower bound on it. Similarly, on the evidence, we are constructing a lower bound. Okay. Now, this maximization now is not only with respect to theta, it is also with respect to q, right? So as I said, you need to find two things. One, you need to find a q that would construct a lower bound on the log likelihood that you would want to maximize. And you also want to find the theta that are model parameters. Is that all right? So you need to find the theta star and the q star, okay, that would maximize the lower bound that we have constructed on the evidence. So what is that lower bound? Lower bound is the expectation of log of p theta divided by q of c given x with respect to x. This is a very important result, okay, that is used in all latent variable models. I mean, this is the framework for latent variable models. So basically, you find out the model parameters theta and also the latent variable parameters q, okay, such that the lower bound that you have constructed on the likelihood function is maximized. Any questions on this? See, note that there are two optimization problems here, right? One optimization problem is over theta, okay, which are the model parameters. The other optimization problem is over q, which is a functional approximation problem, right? It's not over parameters, it is over class of functions. Is this all right? An example for this is, I'll come to you, Vivek. Example for this is what is called as a Gaussian mixture model or a GMM. I'll not go into the details of GMM, okay? But just tell you what P theta of x is, as usual, a latent variable model, which is okay, where P theta of x and z is given by I can write it. Okay, I'll write it this way only. Oh, hold on. Z, okay. You have alpha z's, the normal distribution. So this is a GMM, right? It's a P theta is a linear combination of multiple Gaussian distributions. Okay, so there are okay, let me write it z equal to 1 through m, so the discrete model, right? Yeah, so there are m Gaussian distributions and your model is a combination of m Gaussian distributions. Now theta, okay, will be set of m alphas, alpha 1 through alpha m, okay? And for every Gaussian you have one mean vector, so you have m such mean vectors and you have m sigma vectors. That is your parameters that you would want to estimate in a GMM. How is it done? It is exactly done by solving this optimization problem, no, which is theta star and q star. Okay, so the way it is done is alternatively, okay, solve for theta star and q star. Here you need to solve an optimization problem with respect to both theta star and q star, right? In a GMM, you alternatively get q and theta star. Now, what can be shown as the optimal q star, okay, which would maximize the elbow, okay, can be shown to be equal to simply the posterior distribution. That's all. Okay, so now maybe you can take this as a homework or make it in a TA session. So the optimal Q distribution, right, that would, for this, right, here, when we constructed the lower bound, right, the optimal Q that would maximize this lower bound. By the way, can somebody tell me this? What would be the value of the lower bound with an optimal Q? With the optimal Q, what would be the value of the lower bound with Q star? Okay, f theta of q star will be what? See, what is the maximum value of f theta cube? Am I audible?
Yes, sir.
Did you understand my question? The question is, I've created a lower bound on the likelihood function, no, L theta. Okay, I've denoted that as f theta cube. What would be the maximum value of this? What is the maximum value that this lower bound can achieve?
Log EQ.
L theta, right? Because it's a lower bound on L theta, the maximum value that it can achieve is L theta, isn't it? Do you see that or not? Hello?
Yes, sir. The maximum lower bound will equal L theta. Yes.
Exactly, right? So the maximum lower bound at that point will be simply equal to L theta. Okay. So what I'm saying is it can be theoretically shown that the optimal Q distribution is equal to P theta of Z given X. And for that Q theta, okay, with that Q star, the lower bound that we have constructed is equal to the likelihood value. Okay. Now, once you have gotten an optimal lower bound, what you do is with that Q star, okay, find the next best theta. So now let's call this alternatively solve for theta star and Q star, right? So let's say that we have taken that at theta t, okay. Now Q star at t plus 1, iteration t plus 1 is simply equal to the posterior at theta. So f theta that we have gotten is equal to L theta at that stage. So with that Q star at t plus 1, okay, you find the next best theta t plus 1. How do you do that? Theta t plus 1 is simply the argmax of f that you have computed with Q t plus 1 as a function of theta. That's all. And you keep alternating between these two. So you find a theta, okay, with Q being equal to P theta of Z given X at the previous time. And you use that theta to find your next Q and keep alternating between them. Is this all right? Did you understand this? The only thing that I have not done is I have not told you that y is the optimal Q equal to P theta of Z given X, right? See, that is something that you can take it as a homework or just show that, okay? But yeah, so it is there in my notes also. I mean, it's given in the first lecture of my handwritten notes. Have a look at it, okay? Let's see. This is like of notes. Have a look at it. But yeah, so now basically what we are doing is we are so remember this, right? What we want to do is we wanted to maximize the likelihood. Instead of that, we constructed a lower bound on that, and then we started maximizing the lower bound. And that lower bound depends on two things, theta and Q, right? And we would alternatively optimize between this theta and Q. One example is a GMM, where you first fix a theta and find this Q to be this posterior. Okay. And for a GMM, how do you find this posterior? This can be found out analytically. Now I'll tell you. So P theta of Z given X in the case of a GMM is given by P theta of X given Z times PZ, okay, divided by P theta Z, sum of this thing, right? For Z. This is the definition. Now, what is this equal to? P theta of X given Z for a GMM. This actually means G is equal to one particular J. Okay. Let's say P theta of Z equal to J, and this is equal to J to M. Okay. Now, what is this equal to? The numerator for a given J, GMM is simply that particular Gaussian. Okay. And this is equal to alpha J. Alpha J. And this is simply the sum of G equal to, J equal to 1 to M. J equal to 1 to M. So you have a Gaussian here. Mu J sigma J times alpha J. So this can be found out. Once you find this out, what you do is simply plug that into the lower bound and then maximize that with respect to theta. Right? You get a new theta, use that new theta to evaluate this again. Right? and keep alternating between those two steps. There's a name for this algorithm. Do you know? Does anybody know?
Expectation.
Expectation maximization.
Yeah, this is the EM algorithm. Right? This is the expectation maximization algorithm. This is how you fit a GMM to some data, no? EM algorithm. See, I won't go to showing why EM algorithm is correct and all that. Okay, that I'll skip. But basically, I gave this as an example. I'm running through it quickly because we are interested in looking at VAEs, not GMMs. But yeah, so basically the idea is that this will be common across GMMs and VAEs, all latent variable models, right? Where construct a lower bound on the likelihood and then find the variational distribution and the model parameters through alternative optimizations. That would be same across GMM and this thing. Now, in fact, does all of you know about k-means algorithm? K-means clustering?
Yes, sir.
K-means clustering is exactly EM. So what do you do in k-means clustering? Given data, you randomly assign k clusters, right? And you assign each of the data points to a particular cluster, right? That is this step. Evaluating this, that is this particular step. Evaluating your making your posterior equal to p theta of z given x is actually the assignment step. Okay. Once you assign, you recalculate the means, right? Recalculating the means is this step. Just finding out the theta. In fact, what can be shown is that k-means clustering is a special case of GMM where the variance of those component Gaussians are infinitesimally small. That can be theoretically proved. Anyway, that's a different matter. But basically, the take-home message is that for latent variable models to optimize, what you do is that you construct a lower bound on the likelihood function that you would want to maximize. Okay. And then you estimate both the model parameters and the variational distribution Q together. Okay, that is the take home message. Now, for models like GMMs, right, you know that the optimal Q is p theta of z given x. Okay, and for GMM that can be computed because there's an analytical form. So the question is, we have theta star and Q star to be the maximizers. Okay, we want maximizers with respect to both theta and Q, and we want to maximize the lower bound that we have constructed. Correct. Now Q star is known to be p theta of z given x. Correct. However, what if p theta of z given x can't be computed? See, if p theta of z given x cannot be computed, how do you solve the elbow optimization problem is the question. Does it make sense? For GMMs, p theta of z given x can be computed, and that's why you can do EM. If you cannot compute p theta of z given x, how do you solve elbow optimization is the question that is asked in the VAE paper. That is our preface. Now we want, so now the goal is to estimate the parameters of a latent variable model of a latent variable model for which the posterior p theta of z given x, okay, and be computed. This is our starting point. In fact, the state-of-the-art generative models, which are diffusion models, are also special cases of VAEs. Okay, so it's very important that we understand what VAEs are. Okay, so this is the prelude or preface of why do we need another model. Okay, when there were latent variable models like GMM, it is because while all latent variable models seek to maximize the lower bound on the likelihood with respect to model parameters and distribution over Z, simpler models like GMMs have this advantage that the optimal Q, which is the P theta of Z given X, can be computed analytically. But if there are models for which P theta of Z given X cannot be computed analytically, how do you solve for, how do you estimate the model parameters for latent variable models is the question. Is the story clear so far? So with this, right, I request all of you to read the first and the second chapter of my handwritten notes before coming to the next class. Okay. So with this preface, and if this preface and prelude is strong, we can quickly go to like how VAE solves. VAE actually solves this problem by approximating the variational posterior using a neural network and all that, which we will see in the next class. So please read my handwritten notes, first lecture and second lecture, and come prepared for next class. Okay. Stop here and take questions if there are any. Vivek.
So initially felt like I understood, but there are many things like, so why we used Jensen's inequality, like why do we settle for a lower bound actually?
Because the log likelihood cannot be computed. For latent variable models like GMMs, right, what happens is, see, how do we do maximization? So if we start with the log likelihood, let's say, right? Okay. Let me show that. So now log of P theta of X in the case of GMM will be log of sigma of alpha j, okay, and you have X here, and this is mu j and sigma j, correct? This over j.
Yes.
Now this is sum of alpha j into e power x squared minus mu j squared, so on, right? See,
yes,
if there was sum of, you want to differentiate this with respect to mu and sigma and put it to 0 to maximize this, correct? Now, if there were a sum of log term, then this log and e power exponentiation would cancel each other and you can differentiate. But because you have a log of some terms, here, if you differentiate this, you will not get mu j's in one side and you will not get a tractable equation in terms of mu. So you cannot maximize this.
Okay, the summation of, the log of the summation of
multiple exponentiation, multiple Gaussian distributions. If you differentiate that with respect to one mu, it will not get separated out.
Yes.
Right. So now you need to do something to ensure that this is maximized. So now to maximize that, one way to do it is construct a lower bound. And if you construct the lower bound, EM becomes easier. It is one of the motivations of why do you need to construct lower bounds on log likelihood. Okay. The other thing is again similar thing, log of integral of P theta of X and Z, right? For Z, this is the model. Now, if you do not know how to integrate this with respect to Z because you don't know this distribution, how do you differentiate this with respect to theta? You can't do that. You need another method to optimize for the log likelihood. No, that's why you construct a lower bound and then you optimize for it. See, just you remember why we constructed lower bound on F divergences, right? Because we could not compute the F divergence there because it involved integrals. What we did was we expressed that in terms of expectations that we could compute and then simply used sample estimates to optimize for it, right?
Yes.
Exactly same thing here. Exactly same thing. And you remember that maximizing this is again minimizing the KL divergence. So ultimately, we are minimizing the KL divergence. And to minimize this, this involves integrals with respect to Px and P theta, which we cannot compute. And that's why we are computing lower bounds and expressing it in terms of expectations. that can be estimated using the sample averages. That's the fundamental idea. Okay.
Okay.
Yeah. Aviroop?
Yeah, sir. My question is related to the midterm exam. So the syllabus for it is till the next class or today's class or any specification regarding?
Till the next class. Yeah, there will be one more class before the exam. It will be till that.
Okay, and I mean, just to get some idea on the question, so shall we be expecting coding questions or mostly
No, there will not be any coding questions. It will all be theoretical. So just follow whatever has been said in the class and also the TA session works. That is this. Yeah. Hello.
Yes, sir. I got my answers.
Yeah.
Hi, sir. Ankush here. So I have a quick question. So, sir, we read about this model. Now we understood also exactly how it works internally. So, for practical usage, like where all we can use like image generations or data.
Hold on. You've just started VAEs, right? There's
Yeah.
2 full lectures that will be kept for this, where I can talk about all kinds of applications, how it is used for generative models. Everything will be covered.
Okay, sir. Okay, that is planned. Okay, I was just asking that. Thank you.
Of course, right? I mean, just like we did for GANs, we are just starting it. There's a lot that we need to do. Yeah.
Sure, sure. Thank you.
Simply the preface. Okay. Anything else?
I'm good, sir.
Okay. Yeah. Go on, Srivastava.
Sir, in the assignment, right? I'm just curious to ask, like, since you said there is no report to be submitted, what all things we have tried, we can simply add it in the markdown, right? Because in order to get any valid result, too many things are being tried out from my end. So just want to know.
Come again? What is the question?
Like, so far I was trying assignment questions, so it's not coming directly in the first step itself. Like, a lot of things are being tried out here and there, so we can't just put everything in the notebook, right? So
No, you can. Yeah, markdown statements and every experiment that you tried, just comment it out and put your observations. That will be appreciated.
The problem is, sir, if you are looking for the outputs of those experiments, right? It's taking
No, I don't. Whatever experiments that you tried, just document them. Okay.
Okay, sure. Thank you.
Okay.
And so for assignment, like you said, we should use Google Colab for compute, but there's no free GPU available. So I'm using my company's GPU, and
That's
I'll put
okay.
the.
That's okay. It doesn't matter. Collab if only if people don't have them. Go on, you can speak. You don't have to raise your hands. Class is done. Yeah.
Yeah. So one question regarding the background reading material. Is it okay to read that the machine learning advanced topics by Murphy?
Murphy is okay.
As a
Murphy
good
is a good
introduction.
book. Yeah, it's not. It's actually a very good book. Yeah, you can use Murphy.
Okay, only the portions related to generative modeling.
Whatever we have, see.
Yeah, it's very
taught,
vast. Okay.
Simple thing. Whatever I've taught in class is what your syllabus is. Nothing less, nothing more. Anything that is related to things that I've taught in class is all that I'm going to ask. I don't assume you to know anything that is beyond whatever I've taught in class and also in TA sessions.
Okay. Yeah.
That's all. Okay. If that's all it is, let's meet next week. Okay.
Thank you, sir.
Thank you.
Thank you, sir.
Bye bye.
Thank you, sir.
Thank you, sir.